In this video, I want to start talking about exponential and logarithmic functions. In particular, their derivatives, of course, because we're in calculus. But first, a couple notes on logarithms. I don't know why people freak out over logarithms. It is kind of a weird-ass way of writing things, but you have to write the inverse somehow, and logarithms are the inverses of exponentials. Anyway, so if you say log base a of b is equal to c, another way of writing that is a to the c equals b. I kind of drew the arrows so you can see the circular pattern that might help you remember how to go from one way to the other. If I know a to the c is equal to b, then I can rewrite that as log base a of b equals c. Another thing I want to remind you of or let you know is there are two special logarithms. One is log base e. We never write log base e, we write ln of x, and it is assumed that the base is e. This is called a natural logarithm. You come across this a lot in biology when they're talking about exponential growth of populations, that sort of thing. The other special logarithm is the common logarithm. This is log base 10 of x. If you see just plain log x, assume the base is 10. It's called the common logarithm. We used to use it, not me, I'm not that old. They used to use it when they had slide rules and they had tables of logarithms base 10 to help you with your calculations. You still see log base 10 of x. Most calculators, I think, still have log x, meaning the common log, though I've also seen a calculator that had log of x where they meant natural log, which really messed with my head. Not good to switch that sort of thing. But just something I want you to be aware of. Another thing you want to remember, very important, your laws of logarithms. These will help you a lot. Log base a of m times n, you can split it up into a sum. Log base a of m plus log base a of n. If you have a quotient, log base a of m over n is log base a of m minus log base a of n. If you have m to a power, the exponent can come out front. So log base a of m to the n is n times log base a of m. I am getting tongue-tied. Log base a of 1 is of course equal to 0, and log base a of a is 1. If you want to change bases, something that's more convenient, log base a of m can be rewritten as log base n of m over log base n of a. Though typically, when you do this, you're using natural log, so you can plug it into your calculator. So the derivative. The derivative of a to the x is a to the x natural log of a. The proof for this is in your book. Since the natural log of e is equal to 1, then the derivative of e to the x is e to the x. Bueno cool, we like e to the x. Let's look at y equals 3 to the sine x. The derivative of 3 to the crap is 3 to the crap times natural log of 3. Then we have to do the chain rule. Taking the derivative of sine x, we multiply by cosine x. How about this one? We have x to the 5th times ex cubed. Now we have a product. I will leave the first one alone, taking the derivative of the second, then adding it. I will take the derivative of the first one, leaving the second alone. I don't like seeing this, x to the 5th and x squared in the same expression, separated. Let's bring them together and call that 3x to the 7th e to the x cubed plus 5x to the 4th e to the x cubed. Let's try a quotient. Here we have y equals e to the x over e to the x plus 1. Recall ho-de-hi minus hi-de-ho over ho-ho. So we have the bottom, ho, times the derivative of the top, de-hi, minus the top, hi, times the derivative of the bottom, d-ho, over the bottom squared, ho-ho. That was fun to say. Let's clean this up a little bit. I can multiply the e to the x through on this ho-de-hi to get e to the 2x plus e to the x minus e to the 2x. So there we got it. So that's cool. The e to the 2x's are gone. So we're left with e to the x over e to the x plus 1 quantity squared. Now that we've done exponentials, let's move on to logs. The derivative of log base a of x, as long as a is greater than 0, is 1 over x times natural log of a. That looks like that's a multiplication, but that's just the period at the end of the sentence. If a is equal to e, then you have natural log of x, then the derivative is just 1 over x. Now let's do an example. So we have y equals log base 3 of x cubed plus 2x plus 1. Taking the derivative of this, we've got log base 3 of stuff. So I'm going to have 1 over stuff times natural log of 3 times the derivative of stuff, which is 3x squared plus 2. Let's just scooch the derivative of the bottom over so it doesn't look so lonely over there. So that's our final answer. Suppose we have natural log of x times x squared minus 2 over x plus 1 times x plus 5. Oy vey, that's crazy. We would do 1 over that stuff, then we'd have to do quotient rule, and then we have to do product rule. There's no chain rule in there. That's one nice thing about it. But we're going to make this simpler before we start. We are not going to do it the long gross way, though I know some of you are going to do it on a quiz and it's going to piss me off. But remember, laws of logarithms. If it's on the top, it's going to be a positive natural log of whatever it is. And if it's on the bottom, it's going to be a negative natural log. So I can rewrite this as x is on top, natural log of x. X squared minus 2, positive natural log of x squared minus 2. These two guys are on bottom, so I have minus natural log of x plus 1, minus natural log of x plus 5. This is easy to take the derivative of. Natural log of x goes to 1 over x. Natural log of x squared minus 2, I get 2x over x squared minus 1. Natural log of x plus 1, I have 1 over x plus 1. And natural log of x plus 5, I have 1 over x plus 5. That is so much nicer than trying to do a product rule and a quotient rule and all that mess. Now let's look at another one. Y equals x to the x. Keep in mind, you cannot use a power rule when the variable is in the exponent. How are we going to find this derivative? There's a trick known as logarithmic differentiation. What we do is we're going to take the log of both sides. So I've got log of y equals log of x to the x. Since I have natural log of x to the x, this exponent can come out front. Now let's do the derivative of this using implicit differentiation. I have natural log of y becomes 1 over y dy dx. Over here I have a product rule, x times 1 over x plus natural log of x. Now x times 1 over x is just 1. Let's clean that up first. To solve for dy dx, I multiply both sides by y. Can't leave y in your answer. There was no y over here. That's just weird. Y is x to the x, so we plug it in over here. And that's our final answer. We'll be doing more of these funky logarithmic differentiations, in addition to finding the derivative with exponentials and logarithms and everything all mixed together.